Welcome everybody in today's webinar in the IPCOS webinar series. Maybe a few practicalities to start off. You have joined the audio through computer. At the end of the webinar there will be an opportunity to ask questions, or actually we will answer them then. You can ask questions throughout the webinar by using the chat panel in your WebEx window. Okay. My name is Leon Arians. I'm hosting today's webinar. Normally you would have expected probably Christian Moons to host this, but he's not available to host it today, so I'm filling in for him. The actual webinar will be given by Leo Huisman. Leo has been working for IPCOS since 2004, and he has been participating in and leading many APC projects in the glass industry, various refinery units, ammonia plants. We won't be discussing APC in this webinar, but in fact he will be talking about using the derivative action in PID loop tuning. Leo.
Okay. Thank you, Leon. Welcome to this seminar. So this this seminar is about PID control. And specifically we will zoom in on the derivative part of the PID controller, because that is the part that is least used and least known. So we think it is important to address that, because in some cases the derivative action actually adds something, it gives some benefits. So hopefully this seminar will contribute to your understanding about that. First I will give a brief introduction to IPCOS, our company, and after that I will introduce PID control. I assume you are aware of PID control because you joined this seminar, but anyway, I think it's good to give an introduction first to discuss the different parts of the PID controller and what they do. So we will zoom in on the behavior of that control algorithm, and we will address why people are usually afraid of the D action, the two main causes for fear of using it, and we will discuss how we can deal with those. And we will end with some examples to illustrate how it might help. So IPCOS is a services provider. So actually we have two business units, and this webinar is organized by the business unit that helps optimizing the control of plants, and we are working on studies and audits in the control, in process control, but we also do benefit studies, benchmarking. So we analyze the process and see what benefits can be achieved by optimizing the plant. We also work on PID tuning, base layer optimization. So sometimes that also means changing the structure of the base layer control. Alarm management is something we work on as well since a few years. And of course, several people out there will know that we do advanced process control as well. There we use a multivariable control process controller to optimize the entire plant, and we make use of a optimized base layer control. So part of our work is to optimize the base layer first in those projects, but we will not address that, as Leon already mentioned. And we also give training in PID control and also advanced process control. So that's part of the work we do. We are people organization. So our added value is in the people, in the team. So the people that work for IPCOS bring the added value. It is important for the type of work we do to have knowledge about the process and about process control. So we think it is important to show your team as well on the slide for that reason. We will now turn to our topic of today. So we will talk about PID control, and as most of you will probably know, the P stands for proportional in the PID name, the I for integral, and the D for derivative. And that's typically also referred to as base layer control. So the base layer control in a chemical plant is the whole bunch of PID controllers that together control the plant, and a PID controller typically only controls one variable. Sometimes multiple PID controllers are used to tackle more complicated control problems, but they are single input, single output. PID controllers are really the vast majority of those single loop controllers that you see out there. I only saw in one instance in my work internal model control being used instead of PID control, but that was really an exception. They are part of the DCS system or PLC, so many of those PID controllers are run inside the DCS system, and typically they operate in the sub-second region, so they are fast in comparison to the advanced process control that I mentioned earlier. So as I said, these controllers are single input, single output, so single loops are usually the type of control problems that are tackled by a PID controller, and those controllers are very good at that, provided that they are tuned properly. One of our other webinars held by Edwin Waiting addresses the importance and the added value of tuning your PID controllers and regularly checking whether the tuning is still okay. So yeah, please refer to that webinar as well if you are interested in a more general discussion about PID control. So as I said, sometimes there are also more complicated structures in your DCS system, like cascade controls or ratio controls. Sometimes nonlinearities have to be dealt with using linearizations in combination with the PID controller. So the single loop controllers are the simplest ones, but there are more complicated ones as well. So now before we continue, I have to dive a bit into the algorithm of the PID controller, because it helps us to understand what different versions of the PID algorithm can be found, and that's also important especially in relation to using the derivative action. So you see that the three different parts are in there. So we have the proportional part, which is proportional to the either the PV or the error. The integral part is a summation of the error over time. So if there is an offset, if the error is constant, the integral keeps growing until it approaches the set point again, and then the value of the integral part will become smaller over time again. The derivative part is related to the rate of change of the PV or the error, and that helps to anticipate to changes in the future. And that's the reason the derivative part was added to the controller, so that the controller can benefit from predicting where the PV is going, because the slope, initial slope shows you that in the direction the PV is moving in at the moment, and if that tendency stays the same, then it helps to already compensate for that change in slope. You see also the A and B part in the block diagram, and these are parameters to determine whether the set point is also taken into account in the proportional part of the controller or the derivative part of the controller. So here's an example, or two examples, for Honeywell and for Yokogawa. So for different values of A and B in the block diagram, you get actually the equation types that are present inside those DCS systems. So if you choose equation A in a Honeywell PID controller, that means that A and B are both 1. And that means that the proportional part of the PID controller and the derivative part of the PID controller work on the error. If on the other hand you would choose equation C, that would mean that A and B are both 0, and then both the proportional part and the derivative part only act on the PV, and the set point is not taken into account in those two parts. That means that if you change the set point, initially only the integral part of the controller will do something. So it's important that you are aware of that, and it's important if you are going to tune a loop that you know what type of algorithm is used. It's also important that you think about the use of the algorithm that is active at that moment. Is it really fit for the purpose you have for that particular loop? And of course, if it does not fit the purpose, then it's better to change the equation. And be aware that if you use any software tool to tune your loop, that you select the correct algorithm in the software, because the outcome of the calculations will of course be different if you change the equation type. And in some DCS systems there are also automatic settings where the equation type changes if you change the mode of the PID controller. So if you change from cascade to auto, for example, in Yokogawa, and you have chosen automatic as the equation type, then it will change from PI on the error for cascade to I on the error only for in automatic. Because in case of cascade, the controller has to follow a set point that comes from an external source, from another controller, and in that case you want the controller to be able to follow the set point more closely. So let us now look at the different actions, the different parts of the PID controller. So here we see a response to a set point change, and we also see the effect of a low disturbance. So some stepwise disturbance that may be caused by a valve that someone opens downstream or upstream in the process, and that causes a stepwise disturbance for that particular PID loop. And for both, we will look at what the different parts of the PID controller do. So the blue signal is the set point, the red one is the PV, the yellow one is the output of the controller, and the purple one is the integral part, the green one is the proportional part, and the magenta one is the derivative part. So if you look at the set point change, it is, by the way, a process with a delay. As you can see, after the set point has been changed and after the first changes in the output, controller output appear, it takes a while before the PV actually starts moving. So there is a time delay in there. You see that at time 0, only the integral starts acting, because this algorithm is only the I on error and P and D are on the PV. That means that only the integral part starts to grow until the delay has passed, and then the PV starts moving. It's only then when the proportional part and the derivative part start to change. Because during the delay you see that there is a difference between set point and PV. It stays constant. In that moment the integral starts growing and growing and growing, and it keeps growing until the PV changes, passes the set point. The proportional part starts decreasing because the PV rises. Yeah, so the proportional part starts acting in the opposite direction as the integral. The same holds for the derivative part. You see that the slope starts changing as soon as the delay has passed, and it's that change in slope that makes the derivative part go down at that moment. So you see that the build-up of the integral part during the delay period is counteracted by both the proportional part and the derivative part. And it is for those types of systems where you have a delay that the derivative helps to counteract the build-up of the integral part of the controller. So it acts like a brake. Yeah, so the integral part builds up because it wants to push the PV to the set point, and as the set point starts moving towards the set point, and then the action says, oh, it's moving too fast, I'm going to slow it down. And that makes that the derivative part has a stabilizing effect, and it removes oscillations. It reduces the overshoot of the response. If we look at the low disturbance, there we see that as soon as the PV starts rising, we have a change in slope. From slope 0, it immediately changes to a positive slope, a positive rate of change. That means that the D action immediately changes value. So it's a step-like correction to that, and that makes it possible to anticipate quicker the effect of the disturbance. As you can see, the derivative part is the first one to respond to that change in the PV. So if we remove the derivative part from that same controller, we see indeed that the response becomes more oscillatory. So it has more oscillations around the set point before it settles. And that's the reason a derivative part is a useful addition to the PID controller. If we now go to the proportional and integral on error and only the derivative on the PV, then the response looks different. What we see here at the moment the step in the set point is made is that the proportional part immediately jumps to the proportional gain times the change in set point that was made. Because the error changes instantly to that new to that non-zero value, so the proportional part immediately changes as well, and you see that it's during the delay the PV still doesn't move. The set point is also constant, so the proportional part stays constant during that time. At the same time, the integral also starts building up, and we see that after the delay the PV starts rising. At that moment the PV the proportional part starts decreasing, so it starts counteracting the integral part, and we see that here the derivative part is kept 0, and if we look at the response, if we include the derivative part, we see that the benefit is not that clear for from the derivative part, and because in this part, in the set point change, there is already a big impact from the proportional part, which is feed forward part, so it does not cause any oscillation, so you can already achieve the fast response for the set point change by using this equation type. So there's no real benefit to add the derivative part, because the derivative part you would typically use to make the proportional and integral part larger to get a faster response, and use the derivative to stabilize the system, to reduce the overshoot. But that's not necessary if you use the P on error, and if that is something you would do if you want to follow set point changes. For the rejection of low disturbances, the benefits are more or less the same. So why are people afraid of the D? Well, usually it's because the derivative part causes fast changes in the valve movements. So once people start using the derivative part, the valve movements become a bit nervous, and it starts to create a feeling of unease in the control room. Maybe it's a bit like why some people are afraid of spiders. They move so fast, and the same holds for the D in the PID controller, and that's especially the case if you have a noisy measurement. So if you have noise in your measurement, that will be amplified by the D action, and that means that your valve starts moving a lot when you use the derivative in your controller. Another reason people are afraid might be that once they have used the derivative action and someone decides to change the set point, big changes occur in the output of the controller. So the valve makes a very big change when the set point is changed. And that has to do with the equation type that you choose. So if you use an equation with the derivative also on the error, you get a huge derivative kick at the moment you make the set point change. So this is again the same example with the same size in set point change, but you see that the set point change now seems very small because the derivative part is huge at the very beginning of the response. So the message here is don't use an equation type with derivative on error. I really don't see any reason why to use the derivative on the error. Maybe you have examples and then please share them with us where you think it could be beneficial, but I don't see any benefits from that. So do not use that. The other reason is noise sensitivity. So for that it is important to know that many DCS systems have a filter built in the PID controller, particularly for the derivative part. So instead of the derivative part itself only, they also have built in a part for filtering the derivative term in the controller. And that really helps to suppress the noise. So the form where you often see it in DCS systems is that the time constant of the filter is the time constant of the derivative part divided by derivative gain, N. And that parameter can be changed sometimes in the DCS to tweak the filter. So you can see here the effect of different values of that filter parameter, that derivative gain. So the orange one is the derivative action if you have noise on your PV, and then you see that the effect of the on the D action is really large. So the noise in the D action becomes the dominant part of the output variation of your PID controller. And that's something you don't want, because it does not help, it's not realistic to anticipate to those changes. So you see that for different values of the derivative gain, that not only you suppress the noise, but you also get a change in the response of the D action. So if you make your derivative gain too small, you see that the impact of the D action will be smaller, and then you should ask yourself, is there still added value of the D action in my controller, or can I just leave it 0? And therefore you should not filter too much because then you lose the benefit from the D action. So how do we use the D? Well, I mentioned that it helps if you use it for systems with delays. So for fast loops, that fast anticipation does not really help, because for example, for a flow loop, the difference in response, in fastness of response, is simply too small to even see it on the process variables that really matter. So it doesn't really make sense to add it, and you only make the tuning job more difficult. As I said, it's important to use the proper equation type. So don't use D on error. And also the derivative time should be significantly smaller than the integral time. As I said, the derivative part acts as a brake on the control action. And you can imagine that if you put in your car, you put your foot on the gas pedal and at the same time at the brake, and too much, then and you do it all the time, then it doesn't really help you, because you are fighting one foot with the other. And the same holds for the derivative part. If you make the derivative part too large, you lose performance again. So it should only be used to slow down the control action and return to the end value quicker when the PV approaches the set point quickly. And if you have a noisy signal, think about whether the D is really needed, and if it's not needed, then just leave it out of the controller. And if you think you should need it, then you can apply filtering on the PV. So now let's look at two examples. So this is a temperature control loop that I tuned recently. So it's a reformer temperature, outlet temperature. There was no temperature controller before, so the operators set the fuel gas pressure set point, and we installed a temperature controller. So on the right side you see the model that was fit from on step test data. So we did a step test for that particular loop. As you can see, there is a significant delay. So that makes it a case where the action could help. So that's what we did. And if we optimize, we can set, in the tool that we used, we can set robustness criteria. And if we use those robustness criteria, we see that with the derivative action we can get a faster response to a low disturbance. So often the operators changed the plant load, and each time there was a change in plant load, they had to change the gas pressure, fuel gas pressure set point to compensate for those changes in the feed. And so it was important that the PID controller would anticipate to those load changes more quickly. And as you can see, the derivative action helps to get a faster response and at the same time keep the same robustness. So you see the behavior of the temperature after that tuning. So the second example is a boiler that was also recently tuned by us. Sorry, I went too fast. So if we So the reactor effluent of a reactor, hot reactor, was used to generate steam, and there was a valve directly used by a level controller, a valve of the boiler feed water, and we saw that there was an oscillation on that loop, but we also saw that there was not a normal harmonic oscillation on it. That's what you would expect if there is a tuning problem only. And when we changed the integral time, made it larger, so the integral part's less important, we saw that it made it worse actually. The oscillation amplitude was the same, only the frequency became lower. So, and we also saw that the slope was more or less constant up to the point where it really changed direction. So that's an indication that there is stickiness involved as well. And what we did was we made the proportional and derivative part really larger in the controller to make it more aggressive, so that the valve would already start its descent if the pressure, or the level, sorry, reached the maximum, so that on the way it would go quicker on the way down. So in effect you see that the output of the PID controller changes more quickly, and so that the valve also follows more quickly, and those changes in valve position, you don't see them in the level, because the level responds very slowly. So these are the two examples to illustrate that D can help. Are there any questions? Let's see.
Yeah, a few came in, Leo, during the presentation. For all the attendees, you can still ask questions by typing them in the chat window in WebEx, but as I mentioned, a few came in already. One is, how do you optimize the N in the derivative filter that you showed?
It's not really useful to try to optimize that with tuning tools, because it's the effect of the filter factor on the total PID controller behavior is limited. So only if you make the derivative gain too small, so the filtering too heavy, you start impacting the PID behavior in a negative way. And it's also very difficult to optimize that factor automatically. So my advice would be to maximize the derivative gain, so make N as large as possible to keep the benefit from your derivative part, but look at the output variation of your controller to see if the noise sensitivity is still acceptable. That would be my advice. So you could start with the smaller value of N, just to be on the safe side, and increase it to see if you can improve the performance without sacrificing the noise sensitivity.
Okay, thank you, Leo. Another question that came in, can we use the D action in composition control?
I think by that you mean if we can use analyzers as the measurements for if an analyzer is the measurement, can we still use the derivative part? Well, it depends a bit on the type of analyzer you have. I did use the action for pH control, where there was a delay, and the analyzer was reliable and it was a smooth and continuous signal. Often analyzers are discontinuous, so you typically have analyzers where it takes 10 or 20 minutes before a new value comes in. It can be smaller or larger, that delay. And if you would use D-action in that case, that means that every time a new sample comes in, a new change, you get that same kick in the D-action as you would get with the set point change in the D on error equation. Of course, these kicks will be smaller than because the typical variation will be smaller than the set point change that you would make, hopefully. But still, that would give a big problem for the derivative. So I would not use it in that case. Another issue with analyzers is the reliability. So if you get jumps in the signal because your analyzer is starting to break down, then you also have bigger issues with the derivative part in your PID controller. But often analyzers have very large delays, so in principle you would benefit from a derivative, but because of these drawbacks, I would not advise it. And composition control can be hard anyway for PID for a PID controller if the response is very slow.
Okay, I think we have time for one more question. Let's see. What preparations do you need to make before using the D action in the PID controller?
So I already addressed that in my presentation for the largest part. So as I said, be careful with the equation type. So you don't use D on error. Another thing that I would advise is if you have the possibility to use tuning software so that you can see the impact of the D action, that would be very helpful. And if not, at least calculate what the sensitivity will be of your D action. And also be aware that it has to be smaller than the integral time. So don't make the action too large.
Okay. Thank you, Leo. We're going to close the Q&A part here. Can you move? Yep, thank you. If you would like to have a copy of the slides that Leo has used in his presentation, please send an email to christian.moons@epcos.com. The address is shown on the screen right now, and we will send you a copy of the presentation that Leo used. You can watch a recording of this webinar on the IPCOS YouTube channel that you can reach through our website www.ipcos.com. We will put it there in the next few days. Feel free to share a link to this presentation to colleagues of yours who have not been able to attend today's webinar, or if you would want to look back, listen back in on things Leo has discussed, there will also be an opportunity to watch that there. What's left for me is to announce next webinar, which will be held on October 17th between 9 and 10 British summertime. It will be held by Leo Lategan, and it will be on automatic versus manual testing, the pros and cons of one versus the other. I would say learn from the pro how to do this. So it was nice having you in today's webinar, and I hope to see all of you back in the next webinar. Thank you all for your attention. Bye-bye.